thermal energy transfer. Hello, I hope you're having a great day. Today we're going to pick up on our thermochemistry lectures. We're going to be starting on page uh, 12 in your notes, slide number 23. So let's take a look at one of the great big factors that we deal with all the time when we're looking at thermochemistry. And that's this idea of heat transfer, that the heat from one object is going to go to the heat of another, or go to increase the heat of another object that's cooler than it is. So heat goes from where it is to where it's not. We've talked about that in class, about the ability to heat up your kitchen with your stove, but the inability to cool off your kitchen by opening up your refrigerator. And we're going to tie in those terms that we have, our system and our surroundings. So we're going to have one object that we're going to call our system, and we're going to have the other object that we call our surroundings. Now, in the case that you're most used to, we're going to have like a piece of metal, and we're going to heat that metal up. That's going to be our system. And we're going to drop that into a beaker of water. That water is going to surround our system, and so therefore it's going to be our surroundings. So let's think about this without any numbers first. I'm going to bring in first class drawing here. Okay. So without numbers, we're going to keep this very qualitative. We're going to pretend that this is hot. This is a piece of metal or a block or a rock, something that we've heated up really, really hot. And we're going to make the assumption that our water is starting off cold. Now, not so cold that it's going to freeze, but cold, okay? So the initial conditions for what we're dealing with, we'll say our initial temperature there is hot, and our initial temperature here is cold. Now, if I take and I drop this into the water, we know that that thing is going to cool off, okay? So if this cools off, it is transferring heat. It's transferring heat from its system to the surroundings. And because it's transferring that heat, what's going to happen to the water is the water is going to heat up. Now, eventually, when those two things sit together long enough, we're going to end up with a midpoint. They're going to end up at the same temperature. The same temperature, this ending temperature, which we call T final, is going to be the same for both. In the end, they're both going to have the same temperature. Now, this same temperature is going to be called the thermal equilibrium. It's a whole lot of letters. So those two things at the end have the same temperature. Now, we've got to be careful here because the change in temperature for each will not be the same. Why? Because their specific heat capacity, or the amount of energy it takes to heat and cool that substance for each is different. So let's take a look at how we could change this into a mathematical situation. So if I have a block of metal, and say it's 55 degrees Celsius, like our picture, and we submerge it in water that is 25 degrees Celsius. As we said, the metal is going to transfer energy to the water, okay? Now, things we got to consider is the mass of the metal, the mass of the water, and the specific heat of both of those, along with their change in temperatures. But the deal is the heat that one loses, the other gains. Well, what is heat? Well, if we're talking about heat, we say that heat is represented with the letter Q. So the heat of the metal is going to equal the heat that the water is taking in or giving off. Okay, they're going to be opposite values. Now, I think this is a little misleading because who's giving off the heat? The metal. So I like to think of the negative heat or the heat given off from the metal is going to equal the heat taken in by the water. Now, those are the same thing because the opposite values, but in my mind, it makes more sense because we know a negative value means releases heat, whereas a positive value means it gains heat. So that's one thing that the book does that is not my favorite, but that's all they're trying to say there. So what if we could do a calculation? Well, we know how to find the value of M. M is mass. Have a scale, we can do that. Specific heat capacities, remember, this is a chart value that we can use. Delta T, change in temperature. Now, the big key here is delta T is always T final minus T initial. Okay, you always want the final minus the initial. Sometimes that's going to be a negative number. That is okay. That will work out in the end. I'll show you in just a minute. It really does quite nicely. If you don't do it that way, you end up with negative masses and negative specific heats, and that's never a good thing. So let's take a look at the problem they give us where we're to kind of figure this out. Okay. We've got a 32.5 gram cube of aluminum, initially at 45.8 degrees C. And we're going to drop that into 105.3 grams of water at 15.4 degrees C. What is the final temperature of both substances at thermal equilibrium? Okay, wow, that's a whole lot. So first thing I like to do here is I like to set up what data goes with what, because we're going to have to keep two different things straight, our system and our surrounding. So my system here is going to be my aluminum. My surroundings here are going to be my water, okay? And I know from the information they give me that the mass of my aluminum is 32.5 grams, okay? And I know my T initial. My T initial here is 45.8 degrees C. Now, thankfully, unlike our gas laws, we can keep these in Celsius. So if I look at my water, which is what we're dropping it into, we've got a lot more mass on our water, and it's at a lower temperature. Okay. We're trying to find the final temperature. So we're looking for T final for both of those. Now we know, because we're at thermal equilibrium, which sounds really impressive, that we're really just going to be at the same temperature. Okay, well, I don't know what that temperature is, but I can do some kind of investigative thinking about this work to make sure that when I get an answer, it makes sense. Because I know the temperature for my aluminum that's hot, I'm dropping it in cold water, is going to go down. My water, which is cold, I'm dropping hot metal in it, is going to go up. So my T final should be somewhere in between 45.8 and 15.4. If it's not, I've screwed up on the math. Okay, I've got that mental check. Now it says that the Q that the metal releases is equal to the Q that the water takes in. Well, we know that Q is equal to MC delta T. So we need C for both of those. And remember, C is the chart value, specific heat capacity. So we need to look that up on a chart. we see that for aluminum, that's 0.903 joules per gram Celsius. And for water, it's 4.18 joules per gram Celsius. Okay. Now, to give me a little more room to write here, I'm going to add in some notebook paper. So we know the mass of the aluminum times the specific heat of the aluminum times the change in temperature for the aluminum. Notice, because it's a negative Q, I put this with a negative value. That's going to be important. Equals the mass of the water times specific heat of the water times the change in temperature of the water. So I'm going to fill those values in. Now, to clean that up a bit, I'm going to go on and multiply these two together and distribute through here. I'll multiply these two together and distribute through here. Okay. If you get stuck in this and you want to come in and talk to me about this, feel free. But for our sake of time, and if you want to pause it to see if you end up what I get, this is a great time to do that. So now we're going to combine like terms. When we combine like terms, I end up with I'm going to divide both sides to get T final by itself. So T final is going to be 17.5 degrees Celsius. Now I'm going to ask myself, does this make sense? Is this answer somewhere between the initial value of the water and the metal? Well, my T initial for aluminum was 45.8. My T initial for water was 15.4. So yes, is it between those? Yes, it is. However, it's not the average of those. And that's one thing that people really kind of get tripped up on. They're like, oh, okay, I'll just add those two temperatures together, divide by 2, and that's what it is. No, that's not how that works. And the reason for that is the specific heat capacity. This part right here is kind of going to be the maker or breaker. And it makes a whole lot more sense that the water is not going to raise its temperature very much because it's got a super high specific heat capacity. The aluminum, on the other hand, it makes sense that its temperature would drop a lot because it's got a lower specific heat capacity. Okay, here's one for you to try. Here, we are looking at a block of copper. We know its initial temperature. We're going to put it in a beaker of water that's got this initial temperature. At the end, oh, look, this is nice. They give us our final temperature. So let's see if we can figure out what is the mass of copper. Pause the video, work the problem, and then check back with me. Welcome back. Okay, so this is my working of the problem. Notice I'm looking for the mass. This side is my metal or my copper. This side is my water. I solved for M and got 37.9. Again, feel free to reach out to me if you're having trouble with these, and we can work through them. Okay, next up, we will start a new video. See you soon.